Okay, good morning, everybody. My first thing I'd like to ask is how's everybody doing? Is everybody holding up okay? One of the reasons I'm asking is because my intro to computing class for electrical engineers had a similarly low turnout, and I wanted to see if there was a campus-wide or engineering-wide thing that was coming up that kind of was making everybody tired or exhausted that I wasn't aware of. Unfortunately, I'm not a member of the student community, so when things like that might come up, unfortunately I'm not aware of them, but I like to be aware of them so that way I can adapt the work expectation accordingly. So if there's anything wrong, please feel free to speak up or shoot me an email, and I'll be happy to address that. All right, so three quick things. So the memorandum 1 and the project proposal are due on Sunday night. And then if you've read through the project proposal write-up, you see that one of the things that I mentioned is that to make sure to give yourself a few days at the beginning of next week to account for the fact that the exam is going to be on Wednesday. So exam 2 will be on Wednesday. I have the link up. I'm in the process of recording the last few videos that you can use as flip flashcards, kind of like what we did for exam 1. It's going to be similar in format, similar in time frame, so I think you're probably familiar with how it is that the exam is going to go at this point. I also posted the slides for lecture 31. I mean, I do have a lot of slides up in advance, but I've also posted the homework assignment because in lecture 31, we're going to go over B-tree deletion. I'm sorry, not B-tree deletion, red-black tree deletion. And this will allow us to be, you want to take that opportunity to study ahead a little bit and be prepared for the exam. You have that option available to you. Okay, so first I would like to kind of just briefly review and compare the trees that we've been studying over the last few lectures. And we started out with these binary search trees where we had this idea of we have two outgoing nodes, we called it left and right. We were able to use this to sort insertion, and our goal was to come up with this best case big O of n insertion and search and deletion time. However, we encountered this worst case scenario where if we put everything in the same order, what ends up happening is it just becomes a glorified doubly linked list. So our first attempt was to come up with the AVL tree, and the AVL tree had strict balancing mechanisms, and it had a guaranteed big O log n insert, search, and find. But because those were so complicated and you have to do constant balancing mechanisms, it degraded the performance of the data structure. So then our next attempt was, well, let's see if we can create, using a dynamic array, let's see if we can create a heapified structure that allows us to be able to say all the elements that are below a certain node are less than in the case of a max heap or greater than in case of a min heap. It's not ordered, but it would allow us to be able to grab the top element is the minimum or maximum element, depending on the heap. And that allows us to be able to perform sorting, and we can perform limited types of sorting. So I gave that example of how we did big O log of K, and that allowed us to be able to get the K largest elements in a structure, or the K fewest, depending on what we wanted to do. Our next attempt was say, well, maybe we can put in multiple values in a node. So just in case there's confusion, in a hash table, we have key and value, and that's how we use the input and output into a hash table. Since a lot of these data structures were invented right around the same time, sometimes the terminology that are used to describe the data structure can be a little confusing. And so when they invented the B tree, so when this happened, they were using keys into what we've discussed as the term of value. And so it has better insertion and deletion than the AVL tree. We split in half and rise. All the keys, so all the leaves are at the bottom of the tree, and then we delete and use merge and that borrow from previous and borrowed from next. The methods are still a little complex, and it also doesn't have this binary search method that we have all the way back from binary search tree. If we would traverse, there's a worst case scenario where we have to go through several nodes. I showed that at the end of last lecture. So the question is, can we take advantage of what this B tree is doing, which is this local transformation, but not have to perform recursion every single time? And AVL required all these recursions. if we can use these balancing mechanisms like in the B tree, what we can do is we can get a local and efficient rebalancing. So the whole idea is how can we make local, and when you take algorithms, a term you're going to learn is greedy. Can we make local greedy decisions that give us a good enough result? And so this is why I'm going to say that a red-black tree that we're going to present today is known as a relaxed balance, because it's not as strict as a B tree or an AVL tree, but it gives us a pretty good balance. And what we're going to say is going to be 2 times natural log of n plus 1. So it gives us really good thing. Where we pick up on the gain is that we're only doing local balancing mechanisms. And so the inventors of the red-black tree got their idea from looking at B trees. And so their question is, so up to this point, we've studied this idea of a B tree with a maximum degree of 4. That means we have 3 values inside the B tree and 4 child pointers. Right? And so their first thought is, well, what if I have a B tree with a maximum degree of 2? And so they realized that there's some issues with that. We can't split when we only have 1 element. And so they're like, well, maybe if we change the rules a little bit on B trees, maybe we can come up with a different way to be able to represent a binary tree in B tree form. And so what I want to do is I want to present you a slightly different set of rules on B trees, where what we're going to do is when we put in a first element, we're going to put the element in the middle, and we're going to label its color as black. So here I've inserted 2, and what I have on the left is this modified B tree representation. And what you're going to see on the right is what's going to be the eventual red-black tree. So here we put 2 in the middle, and then when I put in 4, it's going to be on the right-hand side, just like a normal binary tree. So what we're going to do is we're going to put it in the other other value there in the slot, and we're going to label that color as red. So now what's going to happen is I want to put 6 into this particular tree. In a normal B tree, what would happen is we'd have 2, 4, and 6. Let me change that. We would have 2, 4, and 6. Now that's what we're actually going to end up having in our B tree up here too. We're going to put 6 in, and we're going to move everything over. This means 4 is going to become the middle, 6 is going to become the right, and 2 is going to become the left. The element in the middle of this B tree representation we're going to have as a color of black, and the other 2 are going to be colored red. Does everybody see that? Now in the what we're going to call the red-black tree representation, what's going to happen is initially we would say 2, 4, and 6, like so. And what we're going to do is we're going to perform a left rotation. Now what's going to end up happening is we're going to change the colors of what we'll call the grandparent and the parent. So the grandparent is 2 and the parent is 4. And then the parent's left child is going to become 2. And so 2 is now going to be red, and 4 is going to be black, and 6 will remain red. So we're going to see here that this black, red, and red matches the black, red, and red here. So let me press the next on the animation. And we're going to see that 6 is going to go in and rotate over like so. Good. Does everybody see that? So now we're going to put in 10. So in a normal B tree, what we would do is we would put 10 to the right, and then we would raise 4 up, and then 2 would be in a leaf on the left, and then 6 and 10 would be in a leaf on the right. Does that make sense? We're going to do the same thing, except when we split them, the elements are going to be in the middle instead of on the left in this representation. So what's going to happen is we're going to have 4 raised up, like so. Then we're going to have 2 over here, and it's going to be in the middle. Then we're going to be over here, and we're going to have 6 and 10. Now 10 is initially inserted on the right, so what we're going to see is that 6 will be black, and then 10 is going to be over here as red. in this red-black tree. So what will happen is we're going to get 10 over here. And then what we're going to do is we're going to see that its parent is red. And then what we're going to eventually define as its uncle is also red. So if I've inserted something and the parent is red and the uncle is red, we're going to see that the color is going to change here, that both of these are going to become black. So that same thing is going to happen in both our modified B tree representation. There's the 10. And then we split it up like so. Does everybody see that? So then I'd have 8. 8 would become on the left of 6. So in the modified B tree representation, it would just be the first value in that right node. And on the right here, it would be here. So they both end up here, and this would be red, and this would be red. Does everybody see that? So now I want to insert 9. So initially what would happen is we would have 8 split, 9 would be over in the middle here, and then it would look like this. Now 10 was initially in the tree, so in this modified representation, 10 is initially going to be here, and 9 will be over here. It would be like if we did a normal binary search tree, we'd initially have 9 here. Does that make sense? So now what's going to happen is we're going to do the same kind of B tree where we're going to do a combining because we're rising up and we have a non-empty tree. So 8 is going to move up here like so. And then the pointers are still going to be here and here, just like we had with a normal B tree. Except when 8 moves up, it's on the right-hand side. So what we're going to see is that 8 is going to become red. 6 and 10 are going to become black. And then 9 is going to be over here as red. All right, does everybody see that so far? So we've already seen one rebalance. And here we start to see that we have certain rules that are coming up. And I want to point them out to you now, but I'm going to formally define them later in the lecture. Every path to a leaf goes through the same number of black nodes. And so what they were doing is that they're saying, okay, the number of black nodes represents the number of middle keys in our modified B tree. And then anything else that happens to be in any of these elements happens to be red. And so as a result, what you're going to see is that the middle element, since the middle element in these are all black, there's no way to go from 8 and then see a middle and then have another red node. Does that make sense to everybody? So one important rule of what we're going to find as a red-black tree is that you cannot have a red node have a child also be red. So now what I want to do is I want to insert 14. We're going to see that 14 is going to go to the right of 10, and it will be a red node to the right. Let me check the chat really quick. Okay, so we have a question in the chat. Why do we make 8 red? So the element here has to be in the middle is black. And then when we move 8 up here, since it's on the right-hand side, we're going to define it as red. And our goal is to have a, okay, cool. All right, so now we're going to insert 11. So 11 should be the one that we're going to split and move up, right? Let me see, 10 will be, like so. And now here's where the interesting thing comes into play for balancing. So here we see that 10 is split up and that the top the top node in the modified B tree is not full. So here's what's going to happen. We're going to combine these two nodes. And what's going to happen is as a result, 8 will be in the middle, 4 will be on the left, and 10 will be on the right. Which means that 8 is now going to be black, and 10 is going to be recolored to red, and 4 will be recolored to red. And what we're going to see on the right-hand side is that that means that 8 is going to be the middle node. So what we're going to see is a rotation like this, where 8 is going to be the new node at the top, 4 is going to be its new left child, and 6 here is going to be the right child, 4. So let's move this over. So we see that when I split this up, it's already causing this to be. So when we move it over, we now see that 4 has left children of 2 and 6. 4 is a red node. 8 is the middle node, so it's going to be the parent of 4 and 10. 10 is now red because it's now on the right-hand side of the modified B tree. And the 2 children that we did when we split everything up remains the same. And we put in 11 and 14 because 14 was initially there. And so just like in a binary tree, we would move it to the left of a currently existing node. All right, does that make sense so far? And then we put in 5, and now I want to put in 7, and we're going to see that 7 goes to the right of 6. And likewise on the modified B tree representation, 5 would go on the left of 6, 7 would go on the right of 6. And what happens is all of the empty values in the modified B tree are places where we can just put values and not have any rotations. And what would happen is when we had the combining and splitting, so the splitting and then combining of the B tree, by having this kind of representation, we could use this logic to come up with a balanced tree where we're only focusing on the local rotations and splits. Okay, does anybody have any questions before I continue on to the formally defining a B tree? All right, so the whole idea behind an actual B tree is that it's a binary search tree where we use locality of relationships to provide a relaxed balanced tree. In this, every node is defined as red or black. And every path to a null pointer must go through the same number of black nodes. Now, what we saw in the B tree is because the B tree maintains the same number of leaves, I'm saying the same path to every leaf, right? And every leaf has at least one element in it. And if it's the only element that's in the middle, we define it as black. Therefore, if we keep these rules, therefore, we will go through the same number of black nodes through every single path. So what's going on here is if we move this back to representing the B tree, this is one specific node in the B tree. This is one specific node. And now here we have a node there. And this allows us to be able to perform that kind of balance. So this is one, oh, come on. So this is one, it's not cooperating with me. So here's one node, that's a leaf, that's a leaf. So this is the root of the B tree representation. So here's also what we define. If a node is red, then its children must be black. So if we compare this to the B tree modified representation, we know that if there's a value in a B tree node, and we've defined it as red, so it's on the left or the right, and it has pointers going to values, this means that one of two things is happening. Either it's pointing to a null node, so we define null nodes in red-black trees as black, or it's pointing to another value. And we know that the middle value must be black, so therefore, red nodes must have a black child. But we can see that a black node can have a black child as well. Okay, does anybody have any questions on this? We're going to go over several examples of this. Red-black trees can be difficult, and I want you to be confident in raising your hand and slow me down if there's confusion. So here I want to go over that the red nodes all have black children, either null, or in case of 15, has children 12 and 19. 9, 13, and 23 are all null. And then all paths contain 2 black nodes to every single null pointer. So what's going on here is that we want to be able to calculate the height of the tree. And because we're inserting these red nodes, and we're correlating it to a B tree, we are coming up with this relaxed balance of 2 times the log of the number of nodes in the tree. That's going to be greater than the height of the root. So this gives us a relaxed balance. So the worst case scenario is that for some reason, let's say 4 was black, and there's 2 right here, and I get rid of all the rest of those. So 4 was black, that's still a valid tree. So here I have 1, 2, and here I have 1, 2, 3, and 4. So that is a valid scenario for a red-black tree. So it's a relaxed balance. But if I were to add in 15, then we would violate that condition, and we would see the rotations come into play, and it would balance it back out. So the whole goal of a red-black tree, by designing it off of the B tree, is like, okay, keep inserting, keep inserting, keep inserting. And then that is a situation where we're going over the size of the node is the same situation as when we would have to split the B tree and rise up. And then when we rise up, we're using that local aspects of it to recombine and rise, to recombine and rise. And that gets us that balance again. So instead of having to do AVL tree where we have to keep track of the balance on the left and the balance on the right on every single iteration, which can cause us problems, we get this relaxed balance and it's good enough. So therefore, a red-black tree with n nodes is guaranteed to have a height of no greater than 2 times log of n plus 1. And now trying to bring back everything to big O notation, especially for now that you all are taking discrete mathematics, this will hopefully make it a little clearer than when I went over it the first time. So we have this function, we're trying to figure out the worst case scenario. And so when I have 2 times natural log of n plus 1, if I set c is equal to 3 and n of 0 is equal to 1, then I can guarantee that the height of the tree will always be less than 3 times the natural log of the number of nodes. So we have this relaxed balance and it will always be less than that. So this is why we can say that it is big O log of n, insert, search, and delete. Wait, does anybody have any questions? Oh, sorry. Okay, quick historical note. So Bob Sedgwick, the inventor of the red-black tree, when they were working on it, he was working at Xerox, and at the same time they're developing this new fancy laser color printer. And when they were printing out their proofs, they're just like, oh, the 2 best colors on the printout on this really cool new printer that they're coming out are red and black. So that, in case you're wondering why it's called a red-black tree, that was just the printer looked coolest in red and black. Okay, so what I want to do is when you're encountering just the red-black tree element, I'm going to show you how these rotations are normally presented and how they're coded up when what we're going to see. When you're working on this on an exam or trying to figure this out, you can pick either way to convey it as long as it takes you to the final red-black tree. So if you're more comfortable, if you realize, oh, B trees, I'm really comfortable with B trees, I really get this split and rise up and combine, it makes sense to me, and you can make that modified change, you'll be able to get a really good representation of this red-black tree. However, if the rotations I'm going to show you now make more sense to you, that would be the preferred approach I think you should take on the exam as well. So in insertion, the very first rule is that we're going to make every node red initially. And then it becomes, well, how do we change things? So here is on the right-hand side is a scenario that I already discussed where we have a parent and what we're going to call an uncle and a child. So in this scenario, what we would be having here is we would have grandparent, let me change the color to parent, uncle, and then I'm putting child as the right child of the parent. So we have some sort of pointer going here to a new B tree node, of which in the middle automatically we have put the child. Does everybody see that? We have a scenario where we initially put it in as red, and then we're going to identify when we want to change colors. And if there's a scenario like this, we're always going to end up changing the color to black. So because of this scenario, because we have this red B tree idea, the other things we have to bear in mind is we're constantly comparing the node on the left and the node on the right and the node on the middle. So here, if I have children, so if I have a child here, I have a child here, that means its parent is going to be this value in the B tree node, right? The value to the right is what we're going to call an uncle. And so we have to be able to figure out a way to be able, when we're here at the child, to be able to know what color the uncle is in any given moment. So as long as we have, yes. Yes, the colors are purely for rotation purposes. Are there any other questions? Let me check the chat to see if anything's come up as well. But yeah, so that's the main purpose of the colors is to ensure the balance. So the very first case, we're going to call it case 0. Case 0 is what happens if the root is red. So here the grandparent is the root of the red-black tree. The root is going to just be changed to black if it's red. And the reason why is because every path goes through the root. If I change the color from red to black, all it's going to do is change the number that you have to go through in every single path by 1, because every single element has to go through that root. So here the first rule is root is red. We just change it to black. And therefore it will not affect any of the other mechanisms. All right, case 1. So this is that scenario I've shown you where the child is red, the parent is red, and the uncle is red. And so what we're going to do in this scenario is we will change the color of the parent and the uncle. And so this subtree now meets our conditions. So you insert that value, and if we had another child over here that was red, well, these would have been changed already. So if we put in a second child, that'll go in as red. The parent and uncle are now black, and we've now met the condition. And the only time we'd have to change this grandparent if the grandparent was now the root of the tree. Does that make sense? So if we put in here, I'm sorry, let me go back here. So if that grandparent was the root of the tree, that would become a black node. So here, now we're changing one specific thing. The uncle is now black. So now we're in a scenario where in our modified B tree example, the grandparent is black and the uncle is black, which means that the grandparent is in a completely different node in the B tree. So here's what we know. We know that the parent, the child, the grandparent, and the uncle is in this specific order. We also know that these are in 2 different nodes, and now we have these here. So what we've done is we now have a child to the left of a parent. I'm sorry, we have the child is in the middle. So we'd have grandparent, we'd have parent, and we want to put child here. So we'd have to figure out some way to make sure that we maintain this balance. So the way this is going to work is we are now going to make the child's left child equal to the original parent. We're going to make the grandparent's left child equal to the child. And so when we move that into a rotation, what you're going to see here is we now have a proper ordering. And then we're going to go to, this will take us to case 3. So, oh, sorry. Case 2 is okay. That's where I thought the slide was. All right. So in case 2, the important thing to bear in mind is that case 2 is not a terminal case. We're going to have to evaluate something else. So what we're doing is we're performing a rotation. We have inserted a value for the child, and we've realized that we have a parent that's also red, and it in this case was a, if you remember from AVL, we call this a zigzag. And on the next slide, I have the opposite scenario where it's on the right, where we have zigzag in the opposite direction. So if I was to rotate this, this would become grandparent, child, parent, and uncle. So now it's going to animate again. And there we go. So both of these take us to this zig-zig notation that will give us for case 3. So in case 3, we have a scenario when the parent is red, it is the left child of the grandparent, and the child is left and is also red. So we have this scenario where we need to figure out is left. So we're going to see that there's a method that I'm going to include in the code called is left or is right. And we have both of them are is left. So that means the child is less than the parent, is less than the grandparent, is less than the uncle in terms of size. And while it's not super visible, you might see that I have a triangle here. So it can be anything. This could be a node or this can be a null. So when we do this, what's going to happen is we are now going to make the parent's right child equal to the grandparent, and the grandparent's left child is going to be equal to the parent's left child here. So you can see here that the grandparent's left child is now here, and parent is now pointing up there. So now what we're going to see is we're going to have a rotation go this way. And now we're there. Now we're rotating right. And then the last step is to recolor the parent and the grandparent. Hey, does anybody have any questions? So what I want to do is I want to go over another red-black tree insertion example. And this time what we're going to do is we're going to get away from this B tree kind of construct that we have and see how it is that we can just actually insert into a red-black tree itself. So here I have 10. 10 is the root. We hit case 0. All nodes are initially inserted as red, and it's the root, so we change it to 10. Next, we're going to insert 15. So what do you think is going to happen here? Let me bring up the chat so people can put in their guesses as well. What do you think is going to happen here when I try to insert 15? Yes. Very good. And we have a question in the chat. So let me bring up the chat so that way it's going to be to the right as red. So very good. So I'm going to bring this over here so that way we can see the responses. So Brandon, you're correct. Okay, so now what we want to do is we want to insert 25. So what do we think is going to happen here? Yes, in the back. Very good. Very good. Okay, so here we have a scenario where, here we have the scenario where the parent is red, the child is red, and what's going on here with the uncle? Does everybody remember the rule with involving null pointers? What the color is? Yes. Null pointers are black. Very good. So we have that case here where we're going to do what you said, which was we need to rotate. So now we're going to make the 15's left child is going to be 10. 10's right child is going to be null because 15's left child was null. So it's going to look like that. And now it's going to rotate over. And so what's the last step? So this is case 3. So what was the last step of case 3? Yes. Yes, absolutely right. So we switched. So the original grandparent was 10. The original parent was 15. So we're going to change the color of the original grandparent and the original parent, like so. Okay, so next we're going to insert 12. So where's 12 going to go? Yes. 12 is going to go to the right of 10. So now what do we have? What scenario do we have here? Let's see if anybody over here on this side of the. Anybody over here know what we're going to do with it? What is this? Do we know what case this is? I'll come to you in just 1 second. I want to see. This seems to be the side that everybody wants to take a nap. That's okay. I want to take a nap too. I don't blame you. But what's going to happen here? What's the scenario that we are going to encounter? We've inserted 12. And so what are we going to do? I want one person over here on your right side of the room to dare to be wrong. I'm not going to shame you. That comes later. Yes. Okay, so what we're going to do is that we have this scenario where this is now case 2, right? So what you want to do is you want to change it, but because 12 is greater than 10, we have case 2, which means we are going to rotate 12 and 10 to get us to that case 3, which is then what is going to be the black node that you want to do. So what's going to happen is, sorry. Here we have that scenario where we're going to change the colors. And then because 15 is a root, we're now going to change that color back. No, you're absolutely right. So far, so good. So now we're going to insert 5. 5 is to the left of 10. And we're in good shape. There's none of the cases that are encountered here. Why do we change the colors instead of rotating a 10 and 12? So the reason why is because we've encountered this scenario where we have the child, it's on the left, 10 and 25. So in order to maintain the balance, this is going to be, if the scenario was here where we had 12 and 10, then we could rotate. But because 15 is black and we have a left red, so it's going to be zigzag, then the thing that we're going to do is we're going to change the colors as we did in that case and propagate it up. So now we have 5. So now we have 4. So what do we have here? We have that case 3. So what's going to happen here is we are now going to say the parent is red, the uncle is red, and the grandparent is black. So first we have case 1, which means we're going to change the colors. And now we're still in good shape. And the reason why is because 1, 2, the path to every single is null. So there we go, we meet the conditions. So I have 1, 2, 3, 4, 5, 6. Natural log of 2 times 6 plus 1, it's going to be 5.61. So the height is 4. So therefore, the condition is satisfied. So 4 should be less than that. So now I want to insert 3. So now I have this scenario where I have red, red, and black. So now that I have red, red, and black, this is where we're going to start doing rotations. So I'm going to rotate 4 up, and we're going to change the color of 4 and 5, like so. So now I'm making 4's right child equal to 5, and I'm making 5's right child was going to be what 4 was. Now that's null. And now I'm going to make 10's left child equal to 4. So now that's rotated up, and we're going to see that we're now going to change the colors of 4 and 5. And so now we have that balance again. So now you can probably figure out what we're trying to do is get a rotation to go to the right. And so I just keep inserting smaller and smaller values until I get it here. So now what's going to happen is now I have red, red, and black. So the red is the parent, red is the uncle, and the child is 2. So what we're initially going to have is a recolor, and now we're going up the tree. And so now I have yet another red node that is the parent of another red node. So that's 10, 4, and 12. And so I point out that we now have violated the principles, but we're recruiting up the tree. So this allows us to be able to identify locations where we can actually move things around. So the 10s is the parent, the grandparent is 15 is black, the uncle, the 25 is black. And so that's case 2, like so. So now I'm going to do that right rotation. And so that gold pointer is coming from the root node. So 10 is now going to become the root. And then we change the colors of 10 and 15. And now we have received that balance. So in previous trees, when we've talked about this in ABL trees, ABL had that rotation every single time. You saw that I was able to put in several elements that were smaller and smaller, and we still met that condition, but I only needed to rotate it after we got to a certain point. And the other benefit of the red-black tree is that we were able to keep local and analyze everything locally as we went up the tree. So instead of having to recursively check every single time, we were able to perform local rotations, and we still have a well-balanced tree here. So what I would like to show you next is this really cool website that was put together at the University of San Francisco. And it's a visualization tool. And you can use this to is if you're studying, you can say 10, and it's going to immediately go through. I say 11. I can do 9, 6. It actually goes through step by step and shows you all the recolors. You can also press pause. So let's say I want to put in 5. And we'd step forward. And you can see what's the choices being made at every single time. So here's node and the parent both red, node is a left child. So now we would perform that rotation, then recolor. Then if I put in 4, then we do the recolor. Now I put in 3. We can step through this again. Now here we have red and red, and now we have this situation where we want to rotate. Now we have red and red again. We recolor and we're good. But now I want to insert 2. So we still have this relaxed balance. So we see that we can still find elements in a relatively short amount of time. So now we have the left red and red uncle. So now we're going to recolor. You see the recolors there, but now we have that same scenario that we had in the slides where we are eventually going to move up. And then we want to rotate. Let me go back 1. So here what's going to happen is that 10's left child is going to become 9, and 6's right child is going to become 10. And then we recolor 6 and 10. and now we have our balanced tree. So you're going to play around with this, and if you want to study ahead, because a B tree deletion will be on the test, we can say let's delete 6, and you can actually step forward, and I'm going to explain how this happens. But the first thing it does is just like a normal binary search tree, it moves an element up, and then what we're going to discuss on Monday will include why that happens. They also have a really cool one for visualization for B tree. If you Google it, it comes right up. And you can set the maximum degree here. So let's say max degree is 4. I want to do 10, 7. And also you can zoom in to do 6. Since you know it's a max degree of 4, if I put in 8, it's going to raise up 7. And then you can keep messing around with that. And the solution that I presented in lecture in terms of how to find the answer will match this visualization tool as well. So if you want to use that to study, you're more than welcome to. So here, that's the final solution if you put in the values that I put in on the slide. Okay, so it's 11:11. There's no way in heck I will get through all the code that I have there. So what I'm going to do on Monday, and so since I figure I can give it all a treat in just a few minutes early. Like, wow, such a great treat. Thanks, Dr. Morton. But I can dismiss a couple minutes early. What I'm going to do is I'm going to go over the deletion. And then after I go over the deletion, which is basically the process of going backwards in the B tree, so how we're doing deleting and combining that modified B tree. And then that will be the last part of what we're going to cover on the exam. The link is up. I'm putting up the last set of questions and the last set of videos. I'm clarifying there were some questions some students had about specifically how to insert into a max or min heap. So I'm going to provide that video to make sure there's clarity to that. And other than that, project proposals are due on Sunday. The memorandum, where basically you're describing how the interview went. And I'm going to have your TAs reach out to you by Monday since they are going to be the project manager, they're going to reach out to you and then you'll coordinate scheduling your weekly meetings. You want to make that on Thursdays or Fridays, so that way you can get as much work done during the week and you can discuss your progress each week. Does anybody have any questions about anything that's going on through next Friday, what the plan is? Okay, one last thing, I will hold office hours during what was normally the lab, so that way if you have any questions about the exam, that's next Wednesday, that's this coming Wednesday, I'll have extended office hours on Monday. All right, on that note, I will see you all on Monday.